Now we have an inequality sign. So this one could be less than 0, or in another case, the other less than sign we can use is less than or equal to. And then on the other side, so instead of using equal signs, we're now using inequality signs. On the other side, can be greater than 0, or it can be greater than or equal to 0. Okay, so let's take a look at this one. Y is equal to x squared minus 2x minus 3. This is what we were dealing with last chapter, and we have an equal sign here. So if we solve it, we know that the zeros are here at -1 and +3. -1 and 3. So we can say the solution, sorry, this thing's skipping. Come on. Solution is x equals -1, x equals 3. Okay. Now, what if we start dealing with something called these inequalities? Well, what happens with the inequalities is that we get an inequality symbol in there. Okay, so for these next two examples, what happens is we've got the same parabola there, but now we're going to throw in an inequality. So for this one, we say x squared minus 2x minus 3 is greater than 0. Okay, so this means that this is for the values of x for which y is greater than 0. So now what we're talking about is above the x-axis. So instead of the solution being 1 point or 2 points on the parabola, it's now entire regions. So where are some of the possible solutions? Anything where the function is above the x-axis, there and there. Okay. If we continue on with this, and we say x squared minus 2x minus 3 is less than 0. Okay, so this is for values of x. For which y is less than 0. So now we're talking below the x-axis. So now we're talking about the whole region of the solution that is below the x-axis. That would include this entire region like so. Okay, so now we're talking about different regions, entire regions where this happens. Okay, so for both of these, when we talk about the solution, here we say in the first one, the solution, where it's working, solution is x is less than -1, so we're just following the inequality symbol here, or x is greater than 3. For this here, we have this entire region in between the two, so we're going to say that the solution for this system is going to be between -1 and 3. So -1, x is less than, +3, but less than -1. Okay. Now, the x-intercepts of the quadratic functions are called the critical points. So we'll say find the critical points of this function. And we can also use number lines to express this type of a solution. So for the number line, what we would just do for that solution that we came up with from above, you have to take a look at it. Now, if this symbol here is less than or greater than, we're going to use circles to figure this one out. Okay, so let's count this in as 0, 1, 2, 3, 4. And then on the other side, -3, -2, -1. Now we know that the range of answers goes between -1 and 3. So we're going to put open circles here, open circle here, and open circle here, and then signify that all the points in between could be part of the solution. So that's how you signify it on a number line. Okay, the open circles means that it's not the point negative 1 and 3 are not included in the solution. So this divides it into 3 regions, right? This first region over here, where x is less than negative 1, and then the middle region here, which is the solution region, x is going to be between negative 1 and 3, and then this third region over here where just x is greater than 3. So 2 non-solution regions and 1 solution region. Negative 1 and 3 indicate these values are not part of the solution, and any numbers between these critical values are a solution to this inequality. Alright, so let's go to our first example with that background information. Here's one solving by using intervals and test points. Alright, this is going to be long, so get ready. Okay, so the first thing we have to do is put it into quadratic form so that we've got 3x squared plus 2x minus 1 is less than 0. Then we factor it. So 3x is 3 is a prime, so 3x and x. 1's a prime, so that's going to go there and there. And we're going to set this equal to 0 because we want to find out what the critical points are. So here my x is going to be equal to 1/3. Over here my x is going to be equal to negative 1. Okay, so we want to test these different regions, right? So we've got a region where we have between 1/3 and negative 1, and we want to start doing some tests. So let's test from negative 1. Let's just test x equals negative 2. Okay, so that's less than negative 1, of course. So we're testing this region and see if it comes out to have a true or a false statement. It's less than 1, so that's the original statement from the question up here. 8 is less than 1. That's false, so we know that that's not part of the solution. Okay. Over here we test something that's between negative 1 and 1/3. 0 is always a good one. So we test x equals 0. 0 squared plus 2 times 0 is less than 1. 0 is less than 1, so we say that's true. That point satisfies the inequality. And then in our third one, we do something bigger than 1/3. So let's say x equals 1. 3 times 1 squared plus 2 times 1 is less than 1. 5 is less than 1, so that's false. So that point does not satisfy the inequality. Okay. So up here we can say that the solution is the number is going to be between negative 1 and 1/3. Okay. Okay, let's roll ahead to the check. Do the check on page 148. Now we can do this by using intervals and test points. The next thing we want to be able to do is move ahead to using intervals and sign analysis. So how does that look? Well, again, it's a little bit of work. Okay. So here we have this, and I guess the first step we want to do is turn this into quadratic. So we have negative 8x less than or equal to negative 3x squared plus 3. Let's bring everything over to one side, and that a value being positive is really helpful. 3x squared minus 8x minus 3 is less than or equal to 0. Then we're going to factor it, right? So again, 3 is a prime, so we can put 3x and x, and 3 as the c value is a prime as well. But for that to work to be an 8x in the middle, this has to be a 3 and a 1. This is a negative, so we'll make this a negative and then a positive. Set this equal to 0 so we can find out where our critical points here. So x is equal to negative 1/3, x equals 3. So we're looking for the values that are negative, that are below the x-axis, right? Because it's less than or equal to 0. So we're going to start testing. Okay, so looking for something that's smaller than 1/3, so we'll say x equals negative 1. Plug it into the equation. We'll plug it into the factored form, actually. If we do this, 3x plus 1, x minus 3, and where the x is, we put in negative 1. That comes out to negative 2 times negative 4, which is positive, which is positive. Okay, so that means that region is going to be above the x-axis. What about something between negative 1/3 and 3? 0 is always a good one. So we're going to get a positive times a negative, which is negative. Okay, so that's our negative zone. Let's choose something larger than 3. So let's go up here and say x equals 4. So we'll just substitute that in. We get 13 on this side, 1 on the right-hand side. So that's going to give us a positive answer. So what are we looking for, though? We're only looking for regions that are less than or equal to 0. So these two positive ones we disregard, and we're looking for the answer where the region is negative. So here we're going to say that the solution is the region between negative 1/3 and 3. Now, let me give you kind of an illustration of how this looks using a graphing calculator. Okay, so we're going to go into y equals, and we'll just plug in what we have for our quadratic. So we'll just go 3x plus 1 times x minus 3. And so in this quadratic, because it's less than or equal to 0, we just want the region that's here at the bottom, right? So if you get a little bit confused by these questions, pop that inequality into your graphing calculator. You can see that we're just talking about this region here. Okay, flip over to 150 and try to check. Answers provided for you there. Okay, last example, word problem. So people struggle with this, and the way you get better at word problems is to ask questions, work through them, and get used to the language of the word problem itself. The length of the rectangle is 3 meters wider than twice its width. The area of the rectangle is less than 55 square meters. What are the possible dimensions of the rectangle to the nearest tenth of a meter? All right, so we've got to start defining what some of our terms are going to be here. So let's start with x equal to the width. And then we know that it's 3 meters wider than twice the width, so the length is going to be equal to 2x plus 3. Okay, so length times width. Okay, and then when we put it in here, the area is going to be equal to the length times the width, so that's x times 2x plus 3, and it's less than 55, not less than or equal to, but less than, so we pop that in there. Okay, from there, once you get this as a quadratic, then you're starting to fly. The rest is easy after this. Okay, so I think I would use a graphing calculator because this is really tough to factor. So we'll go second calc 0, left bound, right bound, enter, and we're going to find that one of the critical points is 4.5474. So we'll say that x is less than 4.5. Okay, so we'll just use the positive value there. What if we were to figure out what that is? So we know that the width is less than 4.5. It means that the length is going to be equal to 2 times 4.5 plus 3, which equals to 12 meters. Okay, so we'll multiply 4 times 12, length times the width, is equal to 48 square meters, which is definitely less than 55. So we make a concluding statement at the end. This is less than 55 square meters. So possible dimensions are correct. Okay, again, try the sampler on 152, and I'll see you in class tomorrow for the assignment, also available for